let's start this one off with a sketch. We'll get a XY coordinate system on there. X-axis, Y-axis. And we've got some current flowing along the X direction. Along the X-axis in the minus X direction. It's given as 12 amperes. Then we've got a charged particle that's initially at coordinates 0, I'll call that 0.01 meters. And it's got an initial velocity in the plus X direction. You know, it's only got an X component here. That's the unit vector in the plus X direction. And I'll call that V0, and it's equal to 12.0 meters per second. Okay. And we're supposed to draw the trajectory of it, draw the path of it up until it exits a square box. It's 20 centimeters on a side, centered on the origin. I don't think I've got that perfectly centered, but let's go ahead and fix that. Make it a little bit more centered. So something like that. And it's going to, you know, if there was no force on it, it would just go straight out this side. That would be the trajectory, just a line, a segment extended from here to here. That would be the trajectory. But now this thing's in a magnetic field, which I'll draw in yellow. Let's see, by the right-hand rule for something curly, something straight, I'll point my thumb of my right hand in the direction of the current, and the fingers curl around it such that they'd be going in up here and out down here. And I'm particularly concerned with up here where the particle is. So they're in up here, just to get the idea of the initial force anyway on this particle. And then I'll look at F is equal to Q times V cross B to figure out what the direction of the force is. Now V cross B, I'll get the direction by the initial direction of the force anyway. Point the fingers of my right hand in the direction of the velocity arrow, and then I'm going to rotate the hand. I got the palm facing toward the screen now, so if I close the fingers, they point in the direction of the second vector, the B vector, the into the screen vector indicated by those arrows, and I got the thumb pointing upwards. So V cross B is up in this direction. And furthermore, I got a positively charged particle. The charge is plus 3 point, I'll call it Q equals 3.05 times 10 to the minus 3 coulombs. That's 3.05 millicoulombs, millimeans times 10 to the minus 3. Alright, it's positive, so the force will be in the same direction as V cross B. I'll just label that with the force. Okay, so it looks like the particle, instead of going along a straight line, will be forced to curve up somehow. We don't know how much, whether it be coming out this side or out that side. Note that when the particle is at a position like this, the force will be more like that because the velocity will be that way. everywhere up here the magnetic field is into the page, so in the minus z direction, so the right-hand rule will always result in a force that's toward the inside of the curve that the thing is riding on. So it's this orange dotted line that we're supposed to draw, but we got to get it for real. I just put up an arbitrary one in this case. Alright, so we're given the hint that we need a computer to solve this. I think I want to start off by getting a table going here. So I'm going to I use some tiny time interval, delta t. I think I'm going to start off with a microsecond. So 1 times 10 to the minus 6 seconds, 1 microsecond. And I'll have an index, I'll call it n, and just 0, 1, 2, etc. Actually, I think I might need more room for that, so I'd call it 0, 1, and then 2 down below that. A time, and I'll just let the time be whatever the value of n is times delta t. Now I get the same thing down here. Alright, let's see if I can draw a horizontal line here. For this table. Okay, then I'm going to need, that would be the time corresponding to that value of the index, and then I'll need the position. Alright, this is a two-dimensional problem. This thing is moving through two-dimensional space, and what I'm going to do is treat the x and y motion separately. So I'll have a x position and a y position, x sub n, and a y sub n. Let's see, I'll go ahead and put down the starting values. X sub n, we're at 0, 0.01, so it's a 0.01 meters. I want to see how I am doing here for space. The value of x sub n at 1 microsecond would be the preceding value, x sub n minus 1, so that would be 0 plus the value of v during that time interval, so I actually want it at a half. I call it vn minus a half. So if I'm working at 1 microsecond, that would be a half a microsecond times delta t. So as long as I write it on 2 lines, I got enough room there. Okay, I think start working my way across there. So I'm going to need a v of n minus a half, which on this line, which is where I'm going to write it, would be n plus a half. So this will be y, the preceding value, plus v at n minus a half times delta t. Alright, let's keep on working our way across here then. I'll draw another horizontal line. We're going to need the velocities. So I got v, I call it vx component, the nth value. So it starts out at 12 meters per second. And the next value is going to be, we'll call it the preceding value, v sub x n minus 1 plus a sub x n minus a half. So I'm working on 1 microsecond. That would be the value at a half a microsecond times delta t. This is a subscript. It's a little bit high, so I'm going to write that down a little bit lower. A sub x, and then also sub n minus 1, and then times delta t. V sub y was starting going straight out to in the plus x direction, so the initial velocity in the y direction is 0. And this will be, in general, this will be whatever the preceding value was, so the 0 in this case, plus whatever the acceleration is between from 0 to 1, and our best guess at that, I know it's varying, it's actually varying, but we're going to use the mid value, so I'll call that a sub n minus a half, and then times delta t. Okay, and then we need the acceleration values, but the acceleration depends on the force, which depends on the magnetic field. So I think the next thing I'll get is the magnetic field at that particular time. It's the magnetic field at the location of the particle. So magnetic field has a value everywhere in space, but at the location of the particle, it's into the page, so I'm just given the magnitude of it over here, down here. And B sub n, from the formula sheet, is mu 0 over 2 pi times the current over r. That's the magnetic field. This is the exact thing that's on the formula sheet. That's the magnetic field due to a long straight wire when you're at a distance, at a point, a distance r away from the wire. So in our case, I'll call it B sub n, so the position in question depends on is the position of this particle. It's the victim, and it depends on the value of the index n. So it would be mu 0 over 2 pi times I. Now, this thing remains in the xy plane, so the distance r that the particle is from, call that r, from the wire is just the value of y for that index. So I'll call it y sub n. And that's the magnitude of the magnetic field. It's in the plus z direction. So I think I'm ready to pop that in there. So this will be B sub n is equal to mu 0 over 2 pi. So I'm going to need mu 0 in my list of constants here. Mu 0 is, I think it's 4 pi from the formula sheet, times 10 to the minus 7th. Yeah, 4 pi times 10 to the minus 7th Tesla meters, Tesla times meters per ampere. Okay, so this is mu 0 over 2 pi times I, which is the 12 amps, over y sub n. I think I'm going to need value of y. So I'll make a list up here of the things that I need. And this is over y sub n. Okay. This would be the same thing. This was at time 0. At a microsecond, it'll be the same thing, but I'll be taking this value of y sub n. So just whatever I got in there, I can just copy it down to there. All right. What I wanted to get was the acceleration, and ax at the time corresponding to n is equal to 1. Let's see, we got to figure out what the force is. The force is QV cross B. Let's go ahead and copy that down right here. And from that we'll be getting the acceleration. So the force is QV cross B. And that can be expressed, for our case, it'll be the charge of the particle times the velocity vector. I'll call that, I think I'll leave off the subscripts n for this calculation, just to keep it a little bit shorter, and then pop them in when we actually need the expression for the acceleration. So that'll be the Vx I plus Vyj. Now I know Vy starts out at 0, but when we get up here, for instance, where the particle is moving up and to the right, it's got some y component of the velocity. And we got to cross that into B, which is into the page, which is our minus z direction. So I'll just call it the magnitude of B, which is what I've been calling Bn up there, times the minus z direction would be k with the minus sign. Alright, so we got to do that cross product. F in magnitude, I got I crossed into k gives me a minus j. I think I want to do this term first. J crossed into k gives me I, so I'll do the I term first. So I got q times Vy times the B, and then with a minus sign, j crossed into k. So I have minus q Vy B times I. J crossed into k is I. And then the second term, I got I crossed into k, which is a minus j. And with that extra minus sign, we're going to have a plus. Minus and minus is a plus. So we got plus, and then it's QVX times B. And then that was the j. Minus j. I cross k is minus j, but I got that extra minus sign. Okay, so that's what the force looks like. Draw a little free body diagram. Actually got one going here already. On the charged particle, there's the force, and it's experiencing some acceleration in the same direction as the force. That's the only force acting on it. We're assuming. They didn't talk about any other forces, so we'll assume that's the only force acting on it. And I'll do some of the forces. I'm going to write A. Newton's second law is sum of the forces divided by the mass. And in this case, that's just, there's only the one force, F over m. So I'm going to work in vector notation here. And this is, A is equal to, the force is this thing, minus QVYB I vector plus QVXB J vector, all divided by m. So A vector is minus QVY BI over m. And I'll put that whole fraction the way I want to write it is times I, this whole thing times I, and then plus this whole thing times J. So I'm going to need the charge, 3.05 times 10 to the minus 3 coulombs, and I'm going to need the mass. 8.93 times 10 to the minus 10 kilograms. Check that again. 10 to the minus 10. Right there. Alrighty. And my a sub x would be this piece right here. So a sub x is minus q vy b over m. Oh, and that's let's put the subscripts in here now. So that's Vy, the nth value, the 1 corresponding times 0 here for now, times B nth value, all divided by just M. Okay. And Yn would be this piece, but I'll use Vxn and Bn, so that's plus Vx let's go Q Vx nth value times Bn all over M. Alright. And then this just depends on what Vy is. So you know, here I'd be using for Vy, I'd be using the 0 value. Here I'd be using the one here. And for the x, 0, I'd be using this guy. And then I'd be using this one. So it's just the same kind of expression. So I got position, velocity, and acceleration components, all the x and y components. So essentially done with the table, except I need these halfway points for velocity and acceleration. And to get the acceleration one, I'm going to need the b, so I need a y and a half. So I'll do the half values over here on this same line, but go y at n plus a half. So in this line I'm talking about, the first line was so far everything was at the 1 microsecond, or 0 microseconds, and this would be like at a half a microsecond for my current value of delta t. So y at n plus a half. Okay, this is one of those where you got to get started kind of thing, because what I'd like to use is y at n, and then plus the velocity at the middle of that time interval, which would be like n plus a quarter. But I'm going to use the velocity at that particular, just for this first one. So I'll call that, I'm going to label it Vy0. And then times delta t over 2 for this, to get the velocity, the position at a half a microsecond. But in general, it's going to be the one before it, so I'll call it y sub n minus 1 plus the velocity. Okay, this would be for at half a microsecond. This is like 1.5 microseconds, so I need it at 1, which would just be Vn, but it's the y component. Vyn, the one that's on this line, times the full delta t. Alright. And that's all I needed to get. I needed that for the acceleration. I don't need the x value. So now I need v sub x and y. N plus a half. Alrighty. This is all subscript, and you can think of a comma being in there. See how much room I got. Okay, we seem to be golden here. So this would be Vx and then plus, and ideally for this 0 to a half a microsecond interval, I'd need the acceleration at a quarter of a microsecond, but I'll use the starting acceleration, so I'll just call it AX0, which is the one on this line, times delta t over 2. I think while I'm writing that, this is going to be so similar. I'll go ahead and write it. Okay, so Vy n plus a half is Vy. This is the one on this line, which is the 0. I think I'll go ahead and indicate it since this is a special formula. Vy 0 plus, so it's the one over here plus the acceleration at y in the y direction at times 0 times delta t over 2. Okay, but let's get the ones that going to be more general. This would be Vx n minus 1. I want the value up here, so it's Vx n minus a half. Added 1 to that, I'd be at n plus a half, which is what I'm working on. Okay, so this is the preceding one, and then plus the acceleration, x component, n minus a. No, the one that's good for this time interval, which is the one that I calculated here, the n itself. So we'll go with just a sub x times n, and then times the full delta t. So this was like at a half a microsecond, and this is at 1.5 microseconds. So use the value at a half a microsecond of the velocity plus the acceleration valid for 1 microsecond at the 1 microsecond instant times the 1 microsecond time interval, and that gives me the value at 1.5 microseconds. All right, so this essentially the same thing. Vy n minus a half plus ay n times the full delta t. Alright. I need, what else did I need in here? I need the acceleration at the half-time intervals as well. So, now the acceleration depends on the force, so I'll need the Bn plus a half. Alright, but that's the same expression that we had over here, copying it from right there, mu 0 over 2 pi times I times the y n plus a half, which is this value right here. Okay, so that's actually pretty easy, and then it'll be copied down here. And then the an plus a half, I'm thinking it'll be a similar expression to what we had here. Q Vy n plus a half, so the value over here, and then Bn plus a half, the value right there, and I think that's just all over m. Take a look back. Yeah, all over M. And then the other one, oh, there's a minus sign in there. So make sure we get that minus sign. I think I'll make a little room for it. And that was the AX n plus a half. Okay, and then we still need the Y, and my recollection is that looked quite similar to this one. Except there was a plus sign, where at Vy it was Vx. For the AY, and still got the B n over M. Phew. I think that's pretty much it. I need to be able to replicate this. So, well, the thing is, it'll just be the exact same expression as above, except the Vn plus a half will now be the one beside it over here. Same thing for this one. Okay, so let's move on to the next line. And for n is equal to 2, this will just be a copy. Copy. Yeah, I don't think there's going to be anything new. We just have to copy it down, and then that goes from then on. These are obviously just copies, and copy. Alright. So I think we're ready to substitute this stuff into the spreadsheet and go ahead and create this graph. This is just the y position of the particle, this orange track that I'm trying to create the actual trajectory for. It's just y versus x. It's a y versus x plot. So we'll put this stuff in the spreadsheet and make a graph of y sub n versus x sub n. So I'm going to call this the end of part 1